Good afternoon, everyone. Thank you for coming. Our last pre-seminar for this year. And the best way to end this series of seminars is to bring Alistair here. So I assume that everyone knows Alistair. Alistair didn't send the bio, so everything that I say is from my memory. He did his first degree in Sydney Uni in physics, and then he joined UNSW and worked with Martin. He finished his PhD in 92.
1992, yeah.
1992, yeah. He had huge contribution to intrinsic error concentration, so I think that everyone that still work with this one still use his measurements. He also did a lot of work on surface passivation, and fun of it, people call it the Sproul equation. So if you look on this paper from APL, he did also quite a lot of work in the second gen group, and then he shifted to energy efficiency. And now we save the world by not producing watts. Yeah? Alistair was my co-supervisor, so it's always great pleasure to introduce him. He was great supervisor, so I feel very lucky that I choose him. He was not only great model as a scientist, also as a person, and I think that's one of the few people that I really can say that changed my life and shaped them. That's way. I think that I spoke already too much. Please welcome Alistair.
Well, thanks very much, Ziv, for that very kind introduction. I'll have to not send my bio more often, but so that's good. Well, look, thanks everyone for coming along. Good to have you here for the last hurrah for 2015, and I guess I'm standing now between you and Christmas, so I better not waste too much time and get on with it. Look, I thought I'd just give you a few thoughts around and about this sort of topic area, low and zero energy buildings towards green cities in Australia. Australia, we're moving towards greener buildings, and low-cost photovoltaics is certainly helping us to green our buildings and our cities. But I wanted to have a bit of a broader look at what this means in Australia, and a little bit touch base with a few things that are going on worldwide. Of course, we need to do something about energy usage, particularly in Australia. We're very heavily dependent on the fossil fuels, and we know that there's a huge challenge for us. And well, let's hope that what's been going on in Paris recently is going to be a step in the right direction. But yeah, look, it's been in the wings for a long time, climate change and energy usage. And I guess we really need to be serious about where we're putting the money on this. So this is an interesting, sorry, I should mention where that's from. That's the International Energy Agency 2015 World Energy Outlook report, which they put out each year. There was an interesting free publication, so I just thought I'd mention that one there because people can find it. The special report on energy and climate change. So just a few details there that look at that link, and of course we know that energy is one of the big things that's going to be causing lots of problems with carbon. This is the sort of scenarios that we're looking at. The intended nationally determined contributions for COP21 was sort of before the situation before Paris. That's what people were saying, and that's the sort of money that needs to be spent. Something like $35.8 trillion over that period of 2015 to 2030. So as we move down the pathway to get carbon out of the atmosphere and stop putting it up there, it's the trillions of dollars that we need to be spending. Interestingly, and I'll just have a look at this one, this is the 450 scenario, keeping the ppm carbon at 450. You can see that the expenditure there, I'm just particularly interested to see what needs to be spent on energy efficiency and renewables. Industrial energy efficiency, 1.1 trillion. Transport, big shifts coming in transport. I won't be talking too much about that today, but buildings, 4.6 trillion. Big chunk of money and energy and carbon can be saved in buildings. What else have we got here? We've got the renewables. So similar sized chunks, but when we look at energy efficiency is a big one. So sometimes doesn't get the press it deserves, but I guess that's why I'm going to talk a bit more about it today. So there's the, sorry, I better get it right, hadn't I? Intended nationally determined contributions. That's the scenario that they were talking about. That was the pre-Paris commitments that people had made. So Australia was there as well with our 26 to 28%. I know Australia, we tend to get criticised on not having perhaps strong enough position on carbon, but it's a step forward from what we had at Kyoto, where Australia argued for an 8% increase. So perhaps things will move and perhaps things will change as the politics around this hopefully can settle into something like bipartisan agreement would be a great thing on all of this. But anyway, let's see how we go. There's the IEA's mapping of the gigatons of carbon going into our atmosphere between where we are now and 2030. So even if we stuck to what the internationally agreed targets were before Paris, we're still not going to be flattening out and levelling off before 2030 in terms of carbon. And so the International Energy Agency is saying, what else could we do? Some interesting ones there in the news recently: fossil fuel subsidies, some more renewables, getting rid of inefficient coal, etc. But still big chunks of energy efficiency there. So we need energy efficiency. We need even more of it. So look, I'll talk just. These are some slides I put together for a talk I gave recently, but I'm thinking some people in this room haven't seen this one, so I thought I'd share some of these slides. Just a bit of an evolution of Australian green buildings. The one on the left is a bit of an interesting one. This was just a little bit before my time when I was at Sydney University. I started in the early 80s, but in the early to mid 70s, the architect students thought they'd build an autonomous house at Sydney University, and some interesting stories come out of that. If you ever come across a guy by the name of Tone Wheeler, he will tell you some very interesting and colourful stories of how that student house performed in the day. So that's what green buildings used to look like in the 70s. We thought we had to be totally alternative, etc., perhaps, but fortunately, these days, this is a project we're working with CSR through the CRC for low carbon living. This is a project that CSR put together. This is the sort of thing they want to put out to the marketplace to say, look, you don't need to be living like this, perhaps. You can if you want to, but an 8-star energy efficient design today looks pretty much like every other house on the street, except it could be saving 10, 20, 30, 40 more % on energy, more comfortable in heat wave conditions, more comfortable throughout the year, and quieter, the double glazing, etc., better insulation. All of these things help. I think there is a PV system up there on the roof, just for those of you who are worried. Somewhere up there, I think they've got some nice integrated PV Monia tiles up there on the roof. So look, but not all homes in Australia look like either of these two. More typically, this is the sort of thing that we're dealing with. So older Australian homes looking like this, or perhaps a more typical modern home looking like this. I'm not sure if 3 garages are absolutely necessary, but for some people they seem to think. At one stage my dad was worried that his house only had the single garage, and he wondered if he needed to knock it down and build one with 2, but 3, I'm not sure he's been tempted to go to 3, but look, Australian homes built before 2006, no requirement in the building code for any energy requirements there, which is an issue that I'll talk a bit more in a minute about. It's something that's really driven up, in the end, I believe, driven up our energy prices in Australia because of poor performance of buildings, particularly before 2006, where most of our buildings were built. We are now looking at, rather than having some of the cheapest electricity in the world, we've got some of the most expensive, and I think we can pin it down to poor, inefficient buildings. Also, we've got the largest residential buildings in the world. We hold the gold-winning medal position for largest homes. It's sort of flattening out a little bit. So, 240 square metres is the average from the latest data that you can get from the Bureau of Statistics. Sydney is a little bit bigger than that as well. This is a across Australia average. Sydney holds the absolute number one spot for largest homes. And of course, I think we're 266 new home per square metre, 266 square metres for new homes is the average in Sydney. So we're number one in Australia. If you talk with the Europeans, the French, the Germans, the Swiss, of course, much smaller homes, much easier to heat and cool, lower energy requirements, etc. So challenges there for us in Australia if we're to make our homes more energy efficient. If we keep them this size, well, we've got to really work quite hard to improve the energy. Just a brief history on the building code. Started back in 2003. Probably not really until 2006 did we start to see something like a 5-star minimum for residential housing starting to come through in terms of Energy Stars. 6-star minimum now for new houses, etc. Started in 2010, and that's quite good. I mean, if you look at what's happening in Australia, we're catching up to the world. I mean, California and other parts of the world, USA, some parts of the USA, but Germany, Japan, Europe, UK had building code energy requirements back to the 70s and 80s, mostly the early 80s. But we're catching up, which is good, but we still have a lot of old housing stock, which is poorly performing. So heating and cooling, we'll have a bit of a closer look at that. That's a big chunk of where our energy goes, residential. Water heating, another big chunk, but interestingly, now covered under the building code. So you can't any longer put in inefficient hot water systems, which essentially means we're moving away from an all-electric systems and lighting, etc. Now, these are all the fixed aspects of a building that are covered by the building code. Appliances, refrigeration, cooking, standby, quite a sizable chunk of energy going there. Some discussion at the moment about whether we should be addressing those sorts of things, but in the building code, the feeling at the moment is that all the fixed elements of the building, well, most of those things are fixed. The water heating in particular may be argued that it's not so fixed, and lighting, but they're included at the moment, and that's pretty much in agreement with what's going on around the rest of the world. Interesting to see the change from 2003 up to 2013 in terms of insulation in ceilings. Typically 5.1 R value in ceilings and walls up to 2.8, which is not bad. Much better than the 0 that we had there before. And glazing, we're moving on that, and hot water, as I've mentioned, and lighting, as I've mentioned. Yeah, so there's the insulation requirements, depending on where you are, which climate zone you are in Australia. Reasonable. We're comparable now to other parts of the world, so we've done well to get our insulation requirements improved dramatically over the last few years. And that's a step in the right direction. Great for new builds, as I said. What about old buildings? We'd have to have a look at that. Ooh, now, okay, so people in Brisbane who heard me talk last week can probably doze off at this point, but I thought I'd just sneak in a little bit about admittance and the transfer of heat in and out of a building. One of the things that I've been working on recently is just to come up with a simple way for us to get a better feeling for how we're using energy in a building, particularly heating and cooling, as I better get on and talk about. So, look, what I thought what's interesting is to have a look at a building, and this is Sydney. broken down into a very simple climatic environment. Basically just saying, well, what's the average throughout the year? And that average turns out to be just about 18 degrees. If we average the climate across the whole year, we'd get about 18 degrees constant. We'd put a yearly frequency variation of temperature, the dry bulb temperature there. It's got a swing of about 5 degrees up in the summer, so 23 degrees in the summer, down to about 13 degrees in the winter. So a 5 degree swing around the average. And then on average, what's our daily swing? Well, again, another 5 degrees. So we're getting up from 23, we're getting up to averages in the summer of something like average 28, maybe 19 overnight. In the winter, something like 18 and 8 overnight. So fairly representative of a typical climate in Sydney, of our typical climate here. And why am I interested in this? What I'm trying to do, I want to remove some of the mystery of how heat moves in and out of a building. One of the things that happens with buildings is that buildings with mass, people throw their hands up in horror and think that they have to go to a very large program to solve all the equations that are needed to understand a building. But it turns out that once you've got mass in a building, it actually dampens out the daily swings quite well, okay? So any amount of mass that's reasonable, and that's something we need to work on a bit more, you can find that you've got not too much heat flow in and out of the building if your building is shaded in summer in particular. So you're not gaining heat through windows in summer. So what's interesting is that this is the major driver. This yearly and average temperature is actually the major driver, and that's when the variable or the performance of a building can be pretty much modelled just simply as it's the same as a steady state U value, etc. Anyway, it all works out to say that in the end, how do we model a building? Well, on average, a single resistor is all you need, which is just simply saying that it's all the dynamic components of a building, we can treat it fairly quickly and easily. Better not go into too much detail here because just to quickly show you, this is the sort of thing you can do. Just simply analyse a building as a circuit. There's a wall which we can analyse fully. It's a little more complicated than just a single capacitor. Basically a bunch of resistors and capacitors in series together. No, I haven't got a picture of that, but anyway, it all just works out as standard circuit theory. And so what ends up happening is that this solar radiation, for example, shining onto the wall of a building, on the outside wall of the building, what does it do? Well, it's just simply a current divider. Depending on the resistance between the wall and your outside temperature. This is an AC analysis, so under AC conditions we're just doing superposition and all of that. So we can just set that all to zero internally and externally, just look at the impact of this external radiation, and we can just see that most of the heat will go out through this external resistance here from the surface in terms of heat loss to the ambient. Basically we're just saying, this just simply says you absorb heat on the outside of your building, most of it will go outside, some of it will find its way through the mass and then flow into your building inside. Just superposition, we can use that then to analyse it. So quite interesting, just having a look at this. This is 200 millimetres of concrete, summer conditions. There's the absorbed solar radiation, getting up to around about sort of 400 watts per metre squared for 200 millimetres of concrete. Here's the flow of the heat going out to the outside, which is most of where the heat's going. Here's the flow of heat going into the outside of the wall, and eventually, after a bit of a time lag, we can see that there's some considerable heat flowing through into the building. So, for example, the library tower up here, built back in the 60s and 70s, no insulation on the wall, simply on average, probably on the inside wall temperature, on average 2 degrees above what it would otherwise be if it was a well-insulated building. Now 2 degrees might not sound like much, but in a building where you're talking about keeping it air conditioned at 22 degrees, adding just a couple of degrees on the inside of that wall all through summer, considerable heat load. So of interest to me and other people, because putting solar panels, for example, on the outside of such a building shades it, does a number of things, generates electricity, but also then helps reduce the aircon load from those shaded elements. So there's some numbers. I think this is what would happen if we had a 200 square metre, 17.4 watts per metre squared, constantly flowing into that building on average over a 24-hour period. That can add up to be a heat load on a big building, 83 kilowatt hours of heat. We could add some insulation and get that way down. Some nice little ripples in there. That one's real. That's just the wall deciding how much heat's being lost to the outside. And those ones are probably as a result of the Fourier analysis. But anyway, for those of you in the audience who are pleased that I've stopped talking about admittance, yeah, I don't think I've got any more admittance slides, so you're safe. But I do, just as a warning, I do have some more slides on pool pumps, so I know that'll please some people and maybe not others. But look, I better talk about some of the work we're doing with the CRC. Now, this is the sort of thing that's happening around Australia, and I'll show you some examples from Perth, first of all. This is Josh's house in Fremantle. Josh Byrne is an interesting guy for those of you who watch ABC Gardening Show. He's one of the presenters there. But he's also got a very nice house now that's being very closely monitored and analysed. All the data's freely available on the web, and so you can have a look at it there. Nicely designed house. I'm not sure if they've finished, this is an old photo, but this is the only one they've got. I'm not sure if they've finished their shading yet, and it looks a bit temporary, some of this, so this is part of the build for their veranda. But you can see the PV on the roof, the solar hot water, well insulated, well shaded, 10 star. 10 stars is about as good as you can do. Ideally, no need for heating or cooling. Gets a bit warm in summer, he says at times, but they have internal fans, so that's how they're managing to do it. Here's an example of the sort of thing that happens in Fremantle from time to time in the summer. Quite a few days above 30 and a few above 35. A cool change, or a bit of a cool change, came through eventually. So there's the outside temperature. You can see the house slowly charging up, the thermal mass in the house slowly building up, but staying under 27 or 28 degrees, which is probably bearable. That's the passive design approach. That's how you'd expect a 10-star house to perform. Not a lot you can do if the ambient temperature is spending that much time above 30 degrees. It's going to slowly push the building up in temperature. But anyway, we might come back to that and talk about solar-driven air conditioning. But here's a breakdown of Josh's house. Here's the typical Perth average. Quite a lot on water heating and cooling. What else has he got there? Cooking, lights and appliances. There's your Perth average at about 18 kilowatt hours a day. Josh's house is down around about 11, which is pretty good. Part of the reason that his is perhaps higher than might be expected is that he's got in there, what else is he? He's got a grey water system, he's got a rainwater system, and he's got a bore pump. So he's actually providing most of his water himself, harvested off the roof, and he's actually having to treat that water to get better quality, drinkable quality from his water. So quite a bit of energy going into his pumping and his water. I'm often having chats with him and I'm curious to see if we could reduce that, but he's sort of quite happy with that given that he's providing drinking quality water from his rain tanks. And there's the overall cost of a typical Perth house in terms of importing electricity versus Josh's house. So $1,700 average, down to a $200 bill on average. So we know these days that PV on the rooftop, typically in Australia, 15 cents a kilowatt hour is a pretty good price to be a life cycle price for PV on rooftops. Australia, we're now at the situation where 25 cents per kilowatt hour is a fairly typical residential price. There's a good return on investment if you can use the solar power that you've got during the day Residential, it's a bit of a challenge. Josh points out here, this is after a year of measuring his house. They're using 11, on average, something like 11 kilowatt hours a day. About 5.5 is coming from the grid, 5.7 coming from the PV generated on site. They've got enough PV there actually generating 15.4 kilowatt hours every day. So they're exporting something like 9.7. Now, lots of digits there. They're getting about, they're getting about 8.9 cents per kilowatt hour for exported electricity. So reasonable, but not great, perhaps. So they're exporting their electricity, but they're buying it in at, I think it's 25.9 cents they're being charged on their flat rate. So, of course, PV on residential rooftops, we'll have a look at some examples of when that load occurs. Not always a good match. Storage might be an answer. There might be other answers there as well. Ziv warned me that I probably would have too many slides, so he thought I'd get to 7. He thought I'd get to 7. I think I'm a bit further than 7, but I'm doing all right. I'll keep going. Look, Lockhill Park, this is the Adelaide example, very nice. More compact and dense, probably a little more perhaps medium density dwellings. All sorts of interesting designs in there. They basically gave people a few targets that they wanted them to try and hit in terms of their energy performance, and they were hoping that they could get to something like that, reducing non-renewable energy consumption by 66% or something like that, and greenhouse gas emissions by 74% when measured against the Adelaide average. So they've been able to do that as well, pretty well. There's Mawson Lakes, which is a fairly standard housing development system. There's the South Australian average, there's the Australian average. This is in megajoules per square metre, so you'd have to convert annual energy. But basically, they were able to reach their target. So a 70% reduction. Josh's house is doing pretty well. They've got quite large amounts of reductions there, but these were perhaps less attention paid to the energy, but still doing very, very well in overall reduction. Still the challenge, just thought I'd mention this one. This is a European example. What could happen with existing buildings? Could we retrofit existing buildings? And this is in the Netherlands. Energy Sprong from the Netherlands. Pardon me for the language. Bram could probably translate for us. Yeah. I'll have to get him to translate. I'll do one. I'll get Bram to translate it for me, and we can work it all out properly. But look, this was an interesting project that was aiming at public housing. Often that's a real challenge. How do you do things like retrofit or renovate public housing? What they found was that they came up with off-site solutions. They could come to a house like this one, measure it up, go away, do all of the what they needed to do off-site in terms of building products, and then they would come back, and over a period of 10 days, the occupants could move out. The costs were something like 50 to 60,000 euros, which is fairly reasonable. And basically they went from having perhaps a poorly insulated, poorly performing building. They've got the PV on the rooftop, better insulation on the roof, better insulation on the walls, better glazing. What else have they got? They've got a more efficient boiler, hot water system, etc., etc. All of the things that are needed to make a zero energy house. 10 days, 50 to 60,000 euros. The additional loan repayments are covered by the energy bill. So whatever the people were paying before on energy can now go towards paying off the loan, which is not bad, A challenge, I think, perhaps in Australia, but 50 to 60,000 euros, maybe 100,000 Australian dollars if you could do something like that to retrofit dwellings. Maybe it'll cost a bit more because of the size of our buildings. There's one of the challenges. But anyway, watch this space. Can we retrofit our buildings to zero energy? Do we want to? Is the other question. All right. Yeah, I better get going. Look, here's some work done by myself, Ian McGill, and Hua Fan. Well, most of the work's done, of course, by Hua. But we were able to get a hold of smart grid, smart city data. And particularly over this period of time, we were able to get information from the Ausgrid study that was done. Ausgrid did all of this work, and they're particularly interested in peak, but we were interested in looking at the average household energy usage and getting it broken down. 3,000 houses and units, there's the average, about 19 kilowatt hours a day. Some houses, usually not units, but standalone houses using something like 6 times or more the average, 125 kilowatt hours a day. I'm not sure really where all that energy is going, but we could probably have a guess. We can see, we wanted to break this down and find out roughly where do we think this energy is being used in people's houses. What was interesting about the Smart Grid Smart City data was that there was a survey done where all of the households that were being measured, half-hourly interval data, were also also surveyed, and so they were asked all sorts of interesting questions. So, how many occupants were there? What was the type of dwelling house, of the house, unit, house, etc.? Refrigerators, do they have a pool pump? All of these questions. So we were able to gather together all the responses from these 3,000 houses and then build a model of their energy usage on average to see whether we could predict from the model what factors were influencing their energy usage, the daily electricity, consumption. So occupancy, of course, the more people, that has a big influence. So that's one thing in there. Heating. It turned out that heating homes is a big one. Cooling, not so much, and we'll see why in a minute. The dwelling type, of course, whether you're a standalone house or a residential unit, standalone houses use more energy. The number of refrigerators. Do you have a pool pump? Something like 15% of people have a pool and answered that question with a yes, but it's a sizable chunk of energy, as we'll talk about in a minute. So various other things in there. Air conditioning we'll talk about in a minute, and perhaps I better just keep moving. So look, here's pool pump. There's the raw data. This is the average usage of people who said, no, we don't have a pool pump, is the blue. So that's the actual raw data there, binned out in average daily electricity demand, kilowatt hours a day. And that's the probability essentially going on the vertical axis. Here's the red, is the people who do have a pool. So something like we saw the average shift from something just under the total average of 17 kilowatt hours a day. If you don't say, I have a pool, if you say you've got a pool pump or a pool, essentially, that was a strong indicator that you're going to use considerably more electricity on average. Of course, we can't say exactly that it's to do with the pool. People who say yes to this question happen to statistically use a good deal more than average, but we'll talk about pools a little bit more in a minute. Similarly, if we look at air conditioning types, something like 70%, 3/4 of the surveyed households have air conditioning, 70% of them are split systems, 26% ducted. Quite interesting though to see that this is the ducted, this is the split, and this is the people with no air conditioning. Big, significant change between different households depending on whether they have air conditioning, what type of air conditioning, etc. I'll show some more data on that in a minute. Interesting for us to just have a look now from Ausgrid's perspective. They're interested in this summer peaking. So here is the daily electricity demand in kilowatt hours, getting up to something like a peak of 26. That's January 13th or something like that, 2013, if anyone remembers that day. I think it was a plus 40 degree day in Sydney. The typical sort of weather we get in Sydney when the winds swing around to the northwest and the west for a little bit of time and we start to build up some significant heat. Basically, Alice Springs weather comes to Sydney. And that happens maybe once or twice in the summer. And you can see what happens in the electricity demand. We suddenly go on those very warm days. This is the average of 3,000 houses, very high spikes in electricity demand. Now the rest of the time between sort of, spring, summer, autumn, what we're looking at there is that electricity demand on average is fairly flat, fairly low. Sydney's fairly mild climate. Do you remember that? Oh, I better not spend too much time jumping backwards and forwards. There's Sydney. Most of the time between, here's summer, autumn, spring, summer again, we're reasonably, the average temperature is between 18, 19 to 23 degrees. Sydney on the whole has an average climate that's fairly reasonable. In winter though, we drop down to an average of about 13 degrees, which is where our heat demand really comes from for our buildings. But summer, spring, autumn, fairly reasonable temperatures. Occasional spikes, which is what drives peak demand, but not our average demand. So our average demand looks more, jumping back, our average demand is going to be something a good deal higher, and that's going to, than the summer average, and mostly driven by the what's going on in the winter. So we can see that in the depths of winter we're getting up to more likely 22 or 20 kilowatt hours a day average for these houses. And that's pretty correlated with the cooling degrees days here are the blue, heating degree days, how much heat's required for our buildings, how much cooling's required. Sydney climate, typically more heating required if we just look at the difference between average outside temperature and inside temperatures over the year. That's what it looks like. So heating demand days pretty much correlates with our increase in electricity demand through the winter. Spikes in cooling demand correlate with spikes in our electricity usage. Okay, so that's where we are. A bit of a closer look at the peak periods from winter, spring and summer. Let's start with the summer. If we look, this is the typical sort of thing that happens when we've got Sydney going hot. Remember, this is Sydney and Greater Sydney, Northern Sydney and up into the Hunter Valley as well, covering the Ausgrid area. We can see that maybe it's easiest to see here too, these blue curves are the houses averaged out per household demand, getting up to over 4 kilowatts of demand if they've got a ducted aircon system on those very hot days. If they've got a split system, usually smaller systems, they're still significant demand, but much lower than the ducted. The ducted are whole house systems typically, not able to switch them, zone them perhaps, but they're all on, and particularly when it's 40 degrees outside. And these people down here with no aircon in the summer, significantly lower. So the peaks, this is the sort of thing Ausgrid's very much interested in. Here's the peak coming from the ducted, the split, and the no aircons. That little bump in there is hot water systems coming on at off-peak at about 10 o'clock. So this is a peak that's happening in the evening. Now, interestingly, could we do something about that? Could we install batteries? Probably, yes. People will start to do that. Could we install smart systems that control people, give people the ability to switch their aircon on earlier in the day, move this peak earlier to coincide with solar generation? Why not? Why not? Probably cheaper to do that than to have battery storage put in, or a mixture of the two. Winter, we can still see there's significant electricity demand coming through, which is fairly regular and usual. The mornings and the evening peaks here, where people are switching on their reverse cycle aircon, their ducted systems to warm their homes. Sydney homes, remember though, are fairly leaky. No energy requirements for most of them, so they're poorly insulated, which is why we have big demand for heating throughout the winter season. So look, I've got to be careful here, because I'm going to say, people might be thinking that I'm saying air conditioning is the villain, and that's the usual story. Low efficiency buildings with low efficiency aircon, yes, that's the villain. It's driving our peak demand. It's the reason that electricity prices really in Australia have gone up considerably over the last 7 years. To meet that peak demand, electricity prices have gone up over 50% over a period of only 3 years, not so long ago. So, but interestingly, air conditioning, perhaps there's a role for more efficient buildings, more efficient air conditioning, perhaps. If we look at the most efficient reverse cycle aircon in Australia, it's now getting to the point where a small system like this one, 7 stars, which is nice, has a COP getting up towards 6. This is the climate averaged COP, so a little bit lower than the peak values, but a COP of getting towards 6 for heating and cooling, that's not bad. I think that we're getting to the point where reverse cycle air conditioning is probably a lot more environmentally friendly than burning gas for hot water, perhaps, definitely for heating. So that's, keep an eye on efficient air conditioning systems, best if combined with efficient buildings, because then we don't have to build them so big. And interestingly, the smaller they are, the more efficient they are. So the COPs go down. Here's a 2.5, 3.5, 5 kilowatt system. As you get as you get larger systems, the COP goes down, which I think is most likely related to the fact that these are all the same size hardware. They're just driving them at different speeds. You want different output, you slow things down, the energy losses go down, and you get a better performance. Is there a role here for better efficiency for minimum energy performance standards? Could we insist in Australia that air conditioning manufacturers know how to make COP6 equipment? Why don't we actually have that as part of our energy performance standards? All right, pool pumps. Well, we saw that pool pumps are a big energy guzzler. Sorry, not spelling mistake in there, but typically we could get rid of, just from pumping water around, variable speed pumps. I won't spend too much time on that. We could probably cut down 5 kilowatt hours a day. Pool heating is a topic that a few of us in this room are particularly interested in. Jian Zhao, I'll show some of his recent results soon. But look, heating a pool, even with a solar pool heating system, can chew 6 kilowatt hours a day just in pumping. This previous figure back here, just filtering water, there's now these 9-star efficient variable speed drive pumps. They can save you 5 kilowatt hours a day from maybe a 6 kilowatt hour a day on a fixed speed drive. You could reduce that by, get it down to 1 kilowatt hour a day. Same for these solar pool heating systems though. They're chewing something like 6 kilowatt hours a day, just pumping water up to do their pool heating. A lot better than if you use a heat pump. In this instance, the heat pumps aren't doing so well because you're trying to heat 50 to 60 tonnes of water by a couple of degrees, lots of energy. Same for gas. But interestingly, we've just got some results. We've put a variable speed drive onto a solar pool heating system. Ted Spooner's place, in fact. So thanks to Ted. We've been able to get that down to under a kilowatt hour a day for a solar pool heating system using a variable speed drive. So I think that might be my last pool pump slide, so people can breathe a sigh of relief. Let's move on, and I better keep going. I think I've got a few more slides to get through before Ziv stops me. But just to have a quick look at hot water systems, hot water's a big chunk of energy. Just a few comments from me. I mean, in the past, instantaneous gas and gas storage, this is the current situation, big amounts of energy going in there. Electric storage also, probably from coal powered electricity, this is something that we're starting to see being phased out in Australia. People might be then thinking, well, do I go gas? Because that's the typical response. Solar electric boost, solar gas boost, sadly still in Australia, 13% of our hot water is only coming from solar thermal. That's a figure that's barely changed in the 30 years that I've been looking at it. And that's, I think, a real shame. Whether there's an issue there that photovoltaics has decreased dramatically in price because it's an internationally traded commodity, manufactured at scale. Is there an argument to say the same thing should happen for solar thermal hot water? The local manufacturers in Australia would probably be lining up to take a shot at me, but is part of the reason that we've got high prices in Australia simply the size of the market, the size of the manufacturing that's going on here? It's a question that I'm asking. Start throwing stones now. But anyway, let's see what else could happen. Well, look, back onto heat pumps. These things are starting to appear in the market these days. COP of 4.5. Some people in the market have been burnt by heat pump hot water systems in the past, but let's keep an eye on what's happening with more recent advances. COP of 4.5 is quite impressive. In terms of cost, if gas is our option, gas costs, at least what I'm being charged, 3.5 cents a megajoule. I think that's also what's the typical standard rate. That works out at something like 12.6 cents a kilowatt hour. Once you take into account low efficiency systems or even higher efficiency systems, we're still looking at quite a considerable cost per kilowatt hour of thermal energy for heating hot water. Solar hot water, well, good, but there's the capital required, the installation costs, etc., etc. Heat pumps down on the ground, maybe people would point to them and say they've got high capital costs, etc. But putting off-peak or PV at 15 cents a kilowatt hour into a heat pump, you only need a couple of kilowatt hours a day off your PV system, so probably half a kilowatt of your PV array at home could be enough to power a heat pump. And when there's no sun, you could go to the grid for off-peak to back it up. Interesting to have a look and see. Nice way to store solar power. Some people are even suggesting at 15 cents a kilowatt hour, why not just directly plumb photovoltaics straight into a resistance hot water system? I'm not sure that's perhaps the most cost-effective way to do it, and some of us would feel a bit like that's a waste of a high-value energy, but you know, we'll see what happens. If Martin and Zhengrong keep telling me 5 cents a kilowatt hour is where we're headed, it may be the simplest system. Just simply plug your photovoltaic straight into a hot water. Look, in terms of other buildings, you know, the more efficient, the better. Here's some examples from Melbourne, UNSW, Bligh Street. The Pixel building in Melbourne. I don't know if people have seen this building. It's the people who built it and designed it proclaim that it's the highest LEED, that's an American scoring system, highest scored LEED score in the world. Interesting colour scheme, interesting design. But look, you know, these are the sorts of buildings that are out there. Learning lots from these sorts of buildings. Bligh Street, for example, solar thermal array on the top, atrium, daylighting, solar shading on the outside, etc. All very good. Still things to learn, of course, but these are the sorts of exemplar buildings that are out there. We need to improve all our buildings. More of a challenge in the city, but each time we're building new buildings, hopefully we're learning from what's gone on in the past, although not always easy to share the true performance of commercial buildings, although that's improving. Residential buildings, of course, high rise seems to be, or medium rise seems to be where we're going. We could have a debate and a discussion about that. Is it better to put in some fast trains and relieve some of the pressure on the urban districts in Australia and around the world? Would we be better off, rather than putting more and more people into places that already have lots of people, would it be greener, more sustainable to put in rapid transport systems that people can live where land is less expensive perhaps, revitalise areas that might be in the doldrums at the present time. Anyway, of course, putting PV on the rooftop, you all know the Tyree, very, very nice. Perfect example of what we should be doing. This is just a snapshot which I've probably shown before, but worth mentioning here that most commercial loads look like this. There's the green solar generation, there's the demand, commercial buildings, perfectly suited for solar. We don't need storage. Probably another 10 gigawatts of solar could go in on commercial rooftops in Australia, and that would be a great step forward in terms of greening up our buildings and our cities. Look, I'm going to put the conclusions up there and people can read them through, but I think I better stay in camera. I think I better wrap up there and give you a chance to ask some questions if you've got any. Because if you don't have any questions, I'll talk some more about admittance. But anyway, there we go. Thanks very much. Question, Richard.
Thanks for that threat at the end. But, thanks for that talk, Alistair.
Thanks.
We're also already seeing some signs of electricity and energy service providers, electricity providers in particular, reacting to trickle electricity demand either through energy efficiency or solar by pushing up the prices for just being connected to grids and balancing that reducing costs per that going to undermine the financial benefits of the outcomes you are achieving as they roll out into the community? Is there a risk to implementation?
Yes, look, I think it's a very real risk. Just to repeat the question quickly and briefly, the question is electricity providers are upping their standing charges and lowering their per kilowatt hour charges in response, I guess, to increasing penetration of photovoltaics and energy efficiency. Look, I think we need to have a sensible conversation about how we do electricity and how we do energy in Australia and worldwide. I think we need the grid. I mean, I think if they push things too far, people will start to look for perhaps going off-grid. But I mean, that's going to be a very interesting thing to be doing if you've got 5, 6, 7 days of cold weather in winter, no sunshine, etc., etc. You're going to need to be getting out there and making sure your diesel or your petrol generator, if you're totally off-grid, is working. So I think we need the grid. It's going to be an interesting ride, I think, Richard, to see what happens. I think this is globally something that's going to be happening, that the response of the electricity utilities to increasing efficiency and more PV is going to be an interesting one to watch. I think we've got to find a way forward. I think electric vehicles are going to come at us faster than perhaps a lot of people expect, and I think predictions of photovoltaics show that people usually underpredict something that's going to make a big change. So I think we're going to need the electricity. We could probably use more green electricity on the grid. We can use more efficiency, and we may see that electric vehicles start to pick up some of that decrease that the electricity utilities are talking about. I think my perspective is perhaps we're starting to see a bit of a change. Some of the electricity utilities are starting to put forward the idea that they can provide solar systems for your house, etc., etc. So we may be seeing a shift, or we may just be seeing the start of a long arm wrestle.
More questions? Craig Johnson.
Yes, it's a good argument for retaining the utilities in public hands. But my question was about you showed the energy use for Jacob's house, or
Josh's house.
Yes, Josh's house.
Yeah.
And we're commenting that a considerable portion of it is for pumping water in various systems in his house. But you never, or I don't know because I don't look at this very often, but it seems like the amount of energy that's actually used to maintain mains pressure at the side of the water utility rarely is amortized over the users. When talking about the energy cost, not necessarily the energy price, or how much an individual pays for an energy bill, but in terms of total emissions or energy usage for a given household, is that ever included in the standard house breakdown for energy use? Is what Sydney Water was used to actually maintain mains pressure?
Yeah, look, I'd have to. I had a number in my mind, but I'm not sure if it's 100% correct. But I'll mention it anyway, and we can check it out. The energy that's required to deliver water into your home is probably 1 kilowatt hour or less per day, and the utility absorbs that. It's very hard to beat the energy usage that's going into providing utility water from the town water. I say that because I've tried. Water pumps for rainwater tanks can be incredibly energy intensive. They can use 6 times the energy that Sydney Water uses to provide water. Still less than a desal plant, but of that order. So it's hard to beat. The system at my house that I put in is a very small pond pump that pumps to a header tank and then trickles down into our house. Now that uses about 1/6 of what Sydney Water uses, but I have to turn the monitoring system off. The monitoring system, because it's small amounts of water and it's on 24 hours a day, actually makes me use about twice what Sydney Water uses. So lots of small systems, lots of small monitoring. It's hard to beat Sydney Water. Sydney Water, big pumps, efficient system, few monitoring, etc., etc. So it's a challenge. I used to get excited about rainwater tank and pumping and all of that sort of stuff, but I've put it in the too hard basket. Swimming pools are much easier. They're much more of an energy glutton, and it's a good place to mine energy inefficiency. But thanks for the question.
That was the closest I could get to asking about full consideration.
Yeah,
Sorry.
thanks, Craig. I appreciate it. I didn't pay you.
Now, I've got to ask the question, like, to what extent do you still suffer in this area from a bit of an image problem? I mean, you talk about the hippie house from the 70s, but I mean, I turned on the telly the other day and there was some new show on ABC, and one of the protagonists was a guy who was a passive solar architect, and there was enormous comic mirth drawn from the tortures he put his family through by not allowing the air conditioner to be turned on. You know, is this, you talked about your mainstream sort of version of the housing as well, like and I mean, in Australia, insulation is still equated with people dying in rooftops. It's in roof spaces. Like, you know, like, is the mainstream stuff getting there? Is there such a thing as a mainstream? And
Look, I think it's a good question, and I think, you know, energy efficiency does have some baggage with regards to image, but I think in terms of, say, I think we can have a little bit better discussion these days. Well, I'll confess here, my house has an HVAC system now, because you know, for various reasons. Mostly to do with my better half finally talking some sense into me. But look, you know, what we do is that we can run our reverse cycle HVAC with a COP close to 6. We can run it off the solar panels when we're not at home in the winter and in the summer on a 40-degree day, and you can stay very comfortable from the fact that we're exporting. We use 6 kilowatt hours a day total. 3 we buy in from the grid, and 3 we use off the panels at the moment. But if the sun's out on a 40-degree day, which it usually is, we can just switch the PV over to run the HVAC, and we might chew 2 or 3 kilowatt hours a day, keep the house at 24, and then it'll stay there through the evening, and I can switch off and not contribute to the peak demand, because the air's cooling down, the building's cooled down, pre-cooled. So I don't think we have to be living in caves anymore.
And companies like CSR, I mean, do they see markets? Like, do they have people coming to them? There is a mainstream market for these sorts of houses, like, yet? Or
look, the good news,
they clearly want to do it. It's great that they're doing it.
Yeah, no, the good news for new houses is that you're going to have to meet a 6-star minimum, and if you've got a reasonable designer, you can do better than that. So new houses are probably under control, and it's probably old houses that need retrofitting and renovating that are the real challenge. The question is, do we go there, or do we just put enough, flood the system with PV?
Yeah.
That's the other option.
Cool. Thanks, great.
Yeah, okay.
More questions?
I feel like I'm keeping people longer than they need to be.
So maybe before we thank Alistair, because it's the last talk, let's please thank Rob for all the help on this year. Now let's thank Alistair for great talk like always.
Thank you very much.